right, so what we have here is a projectile problem, and a lot of times the best way to start is just make a sketch. So I have here a cannon on a cliff, and so if I draw just sort of a cliff with a cannon on top, and it's firing a cannonball, and what do we know right now? We know that it lands 95 meters away. So the cannonball lands 95 meters from the base of the cliff, and we know in the course of this cannonball firing, it's going to be in the air for 3 seconds. And that's all they really tell us at this point. So from here, we want to break down, we're going to have to use some of our motion equations. But let's first see what they're asking for. So part A says the initial horizontal velocity of the cannonball. So let's translate that into a variable. What do they want? They want a velocity. So that means they're looking for v. And the horizontal velocity means they're looking for vx. And because it's the initial, they're looking for vxi. So vxi is what we're looking for in this one. Next, we're looking for the initial total velocity of the ball. So we're looking for a v, and it's not horizontal, it's not vertical, it's the total, so we don't write x or y, and we want the total initial, so we'll just call it vi. Next, the height of the cliff. So the cannonball's starting at the top of the cliff, and it's finishing at the bottom of the cliff. So it's changing its position by a certain amount in the y direction. So we're looking here essentially for delta y, although we're going to find that delta y is negative because the cannonball is falling. We're going to want a positive version of delta y. The final vertical velocity. Again, we're looking for a velocity, so automatically that means we're looking for a v. It's a vertical velocity, so we're looking for a vy. And it's the end, so we're looking for a vyf. So it's all about translating and getting what we're looking for here. Finally, the final velocity when it hits the ground. Again, it's a velocity v. It's the total, so it's not vy or vx, but it is when it hits the ground, so we're looking here for vf. So anyway, that's the first part of this, is translating what it's asking for. So the first thing we're looking for is vxi, the speed when it's first fired. So we're going to look for an equation that has something along these lines. And we know t, and this 95 meters is how far the cannonball goes horizontally. So that essentially is delta x. And delta x is 95 meters. So if I look at my equations, I'm looking for something. I'm talking about horizontal motion, where I know time, delta x, and I'm looking for vxi. So this looks familiar here. I know delta x and I know t. And you say, wait a minute, this isn't vxi, this is vx. Well, if it doesn't say specifically vxi or vxf, it's the average velocity in the x direction. And the big thing is, in the x direction, the velocity never changes. So vxi, vxf, and vx are all the same thing. So we can use this equation to solve. So going back, I know that delta x equals vx times t. So I know delta x is 95 meters. I know vx is unknown. And I know t is 3 seconds. So that means vx is 95 divided by 3, or 31.67 meters per second. I'm going to round just a little bit there. So that's the speed in the x direction. So when this ball leaves the cannon, it is going 31.67 meters per second horizontally. Next, they want the initial total velocity of the cannonball. All right, well, when this is fired horizontally, it is not moving vertically at the moment it's fired. It has nothing vertical. So if it has no vertical component, that means that it's the same exact speed. Because the total velocity, we can use this equation that says, oh, I got cut off a little bit. The total velocity squared equals vx squared plus vy squared. And so that's just a Pythagorean theorem. So if vy equals 0, then v just equals vx, is essentially what that comes out to be. So what I can do is say, okay, it's the same speed. All right, the height of the cliff, delta y. So what I'm going to do is I'm looking for something with delta y in it, and what do I know in the y direction? I know time, and I also know gravity. We're assuming we're on Earth. And because this ball was fired horizontally, I can make the assumption that vyi is 0 meters per second. So in the vertical direction, there's no initial velocity. So if I go to my equations, in the vertical direction, this equation has delta y in it. I said vyi here I know. I know g, and I know t. I can now solve for delta y. So I'm going to go back. I'm going to take that equation, and I'll just get some more room here. So delta y equals Vyi times t plus 1/2 gt squared. So we just said that Vyi was 0, so this all cancels out. So that means delta y equals 1/2 times g, which is going to be negative 9.8 meters per second squared, times time squared. We said it was in the air for 3 seconds. So square that, so we get 1/2 times 9.8 times 3 squared, which is 9. So I get delta y equals negative 44.1 meters. And put another way, that means that the cannonball, from the time it was fired, dropped negative 44.1 meters, which means how high is the cliff? The cliff then must be positive 44.1 meters high. So delta y there is not quite exactly the height of the cliff. We just have to make it positive. All right, the final vertical velocity when it hits the ground. So VYF, I want to know how fast this is going vertically. Remember, horizontally, there's no acceleration horizontally, so this is the same as if the cannonball were just dropped. So this can be a little confusing. Whether I drop the cannonball straight down or fire it like this, it's going to have, and that's misleading, that should actually be dropping right away. Whether I do it this way or that way, it has the same vertical velocity when it hits the ground. The fact that it was moving horizontally has no effect whatsoever on the vertical velocity on the ground. So I'm going to find an equation solving for VYF, and that one is right here. VYF equals VYI plus G times T. So VYF equals VYI, which we said was 0 because it was horizontal, plus G, negative 9.8 meters per second squared, times T, which is 3 seconds. So 9.8, negative 9.8 times 3. I get VYF equals negative 29.4 meters per second. And the reason this is negative is because it's going in the downward direction. So that is the final speed, or velocity rather, when it hits the ground. And this should make sense. Remember, 9.8 meters per second squared means every second it accelerates by 9.8 meters per second. So over 3 seconds, it reaches almost 30 meters per second. And again, that's negative because it's falling, but this is a reasonable velocity to expect. All right, and the final question says, what is the final velocity when it hits the ground? So in this case, we have to, when it wants the total velocity, we have to take into account that first it was moving in the x direction a certain velocity, and it's moving in the y direction a certain velocity. So looking back, our x velocity was 31.67 meters per second. So that vector is 31.67 meters per second. That is Vx. And in the y direction at the end, down is 29.4 meters per second. And I conveniently got rid of the negative symbol here. It's actually not going to end up mattering whether I put it here or not, because when I solve for v, the equation is that v squared equals vx squared plus vy squared. So when you square a negative number, it's going to work out either way. So v squared equals 31.67 squared plus 29.4, or negative 29.4 squared. And I'm just going to start solving that for v. So 31.67 squared, that's 1,003, plus 29.4 squared is 864.4. I'm going to add those together, and I'll take the square root. And I get my v, my final velocity is 43.2 meters per second. That's not writing very well. So that's my total velocity when it hits the ground. In other words, if I add the vectors, 31.67 horizontally, followed by 29.4 vertically, this vector, the resultant, has a length of 43.2 meters per second. So it's faster than if it was going in just one direction, but it's not as much as if you added them directly together. And so that is the total velocity. So that was a little complex. I know there were a lot of steps involved there. I suggest you probably pause this as you go through, make sure you understand what I did in each situation. But that is a horizontal projectile problem. So until next time, I am Derek Genova. Have a delightful day.